Hello everybody! Welcome back to Physics 214. Now at this point you should have already watched your videos, well your intro video. At least I'm hoping you have watched your intro video. And we are ready to start chapter 18. Okay? So here in the second semester of physics, we're going to start off with thermodynamics. Once we get through thermodynamics, we're going to then move on into electricity, and from electricity we're going to move on into magnetism, and we're going to wind up the end of the semester with waves. Now, I put waves at the end of the semester because they're more fun. And by the end of the semester, you guys are getting tired on me, and I want the fun stuff at the end to kind of recapture your attention. Okay? Now, in the broadest sense, the study of energy starts with the study of the conversion of thermal energy into mechanical work, thermodynamics. We've already looked at potential kinetic energy, large scale. We're going to change our scale down to the submicroscopic scale. So to understand this submicroscopic scale, we're going to need to understand gases. Okay, so let's look at the world of the very tiny, and let's remind ourselves about some things you are probably pretty familiar with. Okay, solids. Now, remember that a solid has a set shape and a set volume, and it has many surfaces. And that's because there are quite strong interactions, okay, between the particles. So if you think about two things off playing, one against the other, we have the attractions between particles and we have collisions which try to push them apart. In the solid, the attractions are winning. The pull together is stronger than the push apart. Liquids, okay, the particles are further apart. Notice that they're not stuck to each other in a very nice rigid pattern. A liquid takes its shape from the container that it's in. It's got one surface, so it only fills the container to a specific volume, and the particles are moving. Now, they're probably not quite this far apart. They want to stay fairly close together, but they're going to slip and slide past each other. Okay? Lastly is the gas phase. Now, in the gas phase, the particles are really far apart. In the gas phase, the force of collision is much stronger than the attractive forces between the particles. So anytime they collide, they bounce apart. Okay? And this is actually closer than gas particles would be if they were this size. So, in solids, attractions win. The pull is greater than the push. In liquid, they're just about on par with each other. In the gas, the push is much greater than the pull. So, if we think about it, solids are incompressible, okay? Liquids are incompressible, but they're considered a fluid because they flow. And gases are considered a fluid because they flow, but gases are compressible because there's lots of space in between the particles. And the particles are in random, constant motion. Okay? So, certain substances can exist in all three phases of matter. Okay? Mercury, carbon dioxide, water, okay, are examples of things that can exist in all three phases of matter. Cellulose, what paper is made out of, can't. Okay? We know that if I took solid ice cube and I added in heat, I could get it to melt into liquid water. And if I keep adding more heat, eventually I can get it to go from liquid water to gaseous water. Okay? So we know that we can phase change. If we want to go the other direction, we've got to take heat out. So we observe phase changes every day, okay, especially when dealing with water. Carbon dioxide exists as solid, liquid, gas. Okay, but under normal daily conditions, the atmospheric pressure we live in, which is about 1 atmosphere, you only encounter the gaseous phase of carbon dioxide. To get solid carbon dioxide, dry ice, they've got to take it to extremely low temperatures. And if you look at where it has to exist as a liquid, those conditions don't occur naturally on Earth. So if you get a solid block of carbon dioxide, it's going to immediately go into the gas phase. Okay? So in this chapter, we're going to look at some of the phase changes, and then we're going to concentrate on the gaseous phase of matter, because that's going to be important as we study the change from thermal energy to work, because in a heat engine, it is the gas phase of matter that is important. Okay? So, state variables. It's a parameter used to characterize a macro state. Now let me remind you what a macro state is. Macro means big picture. Okay? So it would be describing a gas sample as a whole, or a solid sample as a whole. So that's going to be a macro state. So state variables can describe the sample as a whole. So state variable is a group of state functions that can be used to describe the state of a substance. And state variables are things like temperature, mass, volume, mass density, pressure, moles of a substance, and thermal energy content. State variables are not independent of each other. If you change one state variable, you will change another state variable. Example, mass density is equal to mass divided by volume. Mass is a state variable, volume is a state variable, mass density is a state variable. If I were to change the mass, the volume would have to change to maintain the mass density. Okay? So, gas in a balloon, as you drop the temperature, the volume changes. If you then have a volume change like this, and you know that you have a trapped sample of gas, so the mass doesn't change, that means the mass density would have to change. Okay? Any change in state variable is going to be represented by a delta. So change in temperature, delta T would be Tf minus T final, T final minus T initial, F minus I. A system is said to be in thermal equilibrium when all the state variables have stopped changing. They've become constant. So the macro state of a system is dependent on submicroscopic interactions and behaviors of atoms and molecules that make up the macro system. So we need to understand that submicroscopic world. Now, if you guys have taken chemistry with me, you're really familiar with what I'm getting ready to say, but just take this as a review, okay? So we know that the smallest piece of matter to have unique chemical and physical properties is the atom. There are things smaller than the atom, but they do not have a unique set of chemical properties. They only have unique physical properties. So atoms are the building blocks of compounds and matter as far as we're concerned for doing chemistry. Okay? These pieces of matter are small, atoms are classified by the number of protons in their nucleus. All atoms with the same number of protons display the same chemical and physical behaviors, and we call that an element. Okay? The number of protons an atom has is called its atomic number, Z. An atom of an element cannot be broken down into its parts by chemical processes. So I can't split an atom in a benchtop chemical reaction. Okay, you got to do some extraordinary things. We can pop electrons out, we can add extra electrons in, but that's considered to be chemical. Also associated with an individual atom is its atomic mass number, A. The atomic mass number is the sum of the number of protons and the number of neutrons in an atom's nucleus. Now, let me show you some atomic symbols. Okay? All right. No, I'm fine. I'm just going here. Make sure that I can see. Okay, guys. So if I used carbon 14, this is an isotope of carbon, and it's named according to its atomic mass number. So if E is generic element, the atomic number is always shown as a subscript in front, and the atomic mass number is a superscript in front. So from the symbol, I know that the number of proteins is 6, the number of neutrons is equal to 14 minus 6, so in this case it would be 8. Okay, but this is an atomic isotopic symbol. All right, now let's talk about atomic mass and molecular mass. Atomic mass is the average mass of an atom of an element in atomic mass units. Okay? We know that there are slight variations between atoms of an element. Carbon has 3 isotopes. An isotope is an atom of an element that differs in its number of neutrons. Carbon has carbon 12, carbon 13, and carbon 14. Carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. Okay? So the atomic mass is the average mass, because we usually have just a randomized mixed sample of an element, not specific isotopes. The molecular mass is the sum of the atomic masses of all the atoms listed in the formula in atomic mass units. Okay? Now, the mole is a specific number of atoms or molecules for which the number of atoms or molecules has a mass in grams that is numerically the same as the atomic mass or molecular mass in AMUs. Example, carbon has an atomic mass of 12.011 AMUs. 1 mole of carbon atoms has a mass of 12.011 grams. 1 mole of anything equals 6.022 times 10 to the 23 of whatever it is you're talking about having a mole of. If you had that many water molecules, you could swallow it in a single gulp. 1 mole of water molecules. Okay? It's very small individual molecules and atoms. If you had that many ping pong balls, you could bury the 48 contiguous United States to a depth of a couple of miles. Okay? So, the mole. It's just a number of particles. 6.022 times 10 to the 23. Now, temperature. Temperature, of course, is a measure of how hot or how cold something is. Now, that's a very wishy-washy definition. Temperature is related to average thermal energy content. So, if it's measured to average thermal energy content, thermal energy is the energy that something possesses because the atoms or molecules are moving. That could be translational motion, that could be vibrational motion, that could be rotational motion. And if you think about kind of vibrational motion, remember that the energy is always going back and forth between kinetic and potential. Because as they move out, they move out, they start out moving fast, and then they slow down, and then they stop, and then they start moving back in. Okay? All right. Thermal energy is the sum of all the kinetic energies of all the particles in a substance. So as temperature goes up, the thermal energy content goes up. Or you could say that as thermal energy content goes up, the temperature goes up. They're directly related because temperature is related to thermal energy content. If two objects are at the same temperature, then we can say they have the same average kinetic energy. Not the same total thermal energy content, but the same average kinetic energy. That's because the sample sizes could be different. Okay, think about having a half a cup of water and how much energy you have to put into on a stove to get it up to the boiling point, and if you had 3 cups of water and you tried to bring it up to the boiling point. If you put them on identical burners set to the same setting, it would take the 3 cups much longer to get up to boiling than the other. Okay? Now, absolute zero. It's the point at which all motion stops. It's a theoretical point. Okay, it occurs at 0 K. Temperature in Kelvin equals temperature in degrees C plus 273.15. When we're doing thermodynamics, okay, we're always going to use the temperature in the Kelvin scale based on absolute zero. All right, phase changes. The phase change is a change from one phase of matter to the other, from solid to liquid, liquid to gas, gas to solid, vice versa. One of the easiest ways to cause a phase change is to either add energy into a system or take energy away from a system when the pressure is held constant. Now, if we're looking at phase changes between gas and liquid or gas and solid, pressure can also play a role, but right now we're going to look at where we're holding the pressure constant. So let's look at a graph of temperature versus thermal energy added and see what happens. Okay? So let's look at this. Okay. Now, in this situation, pressure is constant. That's okay. Right there. Now, we're starting down here at like minus 25 degrees C. And notice that as we warm the temperature, as we add in energy with time, the ice warms up, but it stays ice. Once we get to 0 degrees C, all the energy that's being absorbed by the system is going into a phase change, and the temperature remains constant. Because what we're doing is we're seeing a conformational change of the particles, and the thermal energy content is staying the same. The energy that's being put in is going to change the potential energy of the system. Okay? Once everything has been converted over from solid to liquid, all of a sudden the liquid starts warming up because we've changed the potential energy of the system, okay? And now we start changing the thermal energy, the kinetic energy of the system. The system warms up again until we reach 100 degrees C. Then as we put energy in, okay, the temperature levels off again, and it levels off because again we're having a conformational change. We're changing the potential energy of the system. Things are going from being close together to popping really far apart. So the change here, the energy we're putting in, is going to change the potential energy of the system, and then once we get it all into the gas phase, the temperature of the gas will increase. Okay? So, go ahead and keep scrolling down. Let's talk about melting point, freezing point, boiling point, condensation point, and a phase equilibrium. Melting point, freezing point. At a specific pressure is the temperature at which the solid and liquid phases are in equilibrium with each other. Equilibrium here means that for every particle that goes from the liquid to the solid phase, a particle goes from the solid phase to the liquid phase. So if we are at equilibrium and we're not putting any energy in, then the amount of material in the solid phase, the amount of material in the liquid phase are going to stay constant. If we are at the freezing point and I add energy in, then I'm going to see a net movement from solid to liquid. If I'm at the freezing point, melting point, and I am taking energy out, we're going to see a net move from liquid to solid. Okay, any energy we add in or take away changes the potential energy of the system. Now, boiling point, condensation point at a specific pressure. It's the temperature at which a liquid and gaseous phases, I hate to say in equilibrium with each other, but we can do that. At the boiling point, condensation point, if you add energy in, you're going to go from liquid to gas. If you take energy out, you're going to go from gas to liquid. Okay? Now, equilibrium is really not a, well, no, I'll talk about that more later. Phase equilibrium. Okay, 2 or 3 phases can be present in any ratio, and the ratio will be maintained if you are in a phase equilibrium. Okay. Now, besides temperature, pressure can play a role in phase transitions, because as temperature changes, at a given temperature, we can see a change from gas to liquid or to solid, or we can see the opposite, solid to liquid to gas. Now, a phase diagram, okay, is a pressure versus temperature graph that shows boundaries between the solid, the liquid, and the gaseous phase of matter. Lines are where 2 phases are in equilibrium with each other, and the regions of pressure and temperature in between the lines says that you will have 1 phase of matter that exists. Okay? Now, here's a phase diagram for water. Okay? In this region, the dark brown, that's where we have solid water. Okay? This region under here, gaseous water, and in between you have liquid water. Now I want you to notice solid's going to occur where the temperature is lower, pressure is higher. Gases are where the temperature is higher and the pressure is lower, and liquids are always trapped in between the solid and the gas. So it's always solid, liquid, gas if you kind of go clockwise around, even if they weren't labeled. Okay? Along this line is the solid-liquid equilibrium. So if I were to add heat in, increase the temperature, adding in energy, we'd see melting. If I decrease the temperature, I'd see freezing. Now notice down in here, if I go from if I increase the temperature, I don't go into the liquid phase, I go into the gas phase. And that's because of the way the pressure is situated. Okay, this is called sublimation. If we were to go back the other direction from gas straight to solid, that would be called deposition. Okay, condensation here, going from solid to liquid. Boiling, if we go from liquid to gas, you could also call this evaporation. But along that line, since we're talking about the boiling point, melting point line, we use boiling. Now, let me point out a couple of features here. Number 1 is the triple point. Okay, the triple point is where those lines intersect. So at the triple point, all 3 phases of matter exist in equilibrium with each other. You would have to change temperature and or pressure to see a net move in any direction. And notice it occurs at an atmospheric pressure of 0.006 and a temperature of 0.01. Those aren't conditions that you normally see. Okay? But all 3 phases would exist there. That's a triple point. Now up here we have the critical point. What's really interesting at the critical point, notice the line ends above the critical temperature. No matter how much pressure you apply, you cannot see a distinct liquid and gas phase. So we talk about not being able to condense a gas back into a liquid above the critical temperature, the temperature at the critical point. In the region beyond the critical point, in pressure and in temperature. Okay? You get what's called a supercritical fluid. It's not quite liquid and it's not quite gas. When you hit the critical point, the separation between the liquid and the gas phases disappear, and you have a supercritical fluid. They're really interesting, the properties of supercritical fluids. Now, I'll talk about it a little bit more when we look at the carbon dioxide phase diagram in just a second. One thing I want you to notice here, because this is water, is I want you to notice that the solid liquid equilibrium line keeps the isobaric process because the pressure is constant. Okay? It says, what's the final temperature? We're told that the initial temperature here is 900 degrees C. So that, adding 273 to it, is 1,173 K. We want to know T2. Now, I can say that V1 over T1 has to equal V2 over T2. Because we are doing ratios, I don't have to worry about the units. Okay? So V1 here is 300 centimeters cubed. T1 is 1,173 K, and that has to equal 100 centimeters cubed over T2. Now guys, you can flip this. So I can go 1173 over 300 centimeters cubed has to equal T2 over 100 centimeters cubed. Now notice the centimeters cubed is going to divide out, the 100 is going to divide out. So all I need to do is take 1173 and divide it by 3. So T2 is 391 K. Now guys, you'd really screw this problem up if you didn't put the temperature in Kelvin. Okay? So make sure you get the temperature in Kelvin. All right, guys. Now, let's look at an isothermal process. In an isothermal process, we have constant sample size and constant temperature. Okay? So, if we switch from a V1 to a V2, some interesting things go on. Namely, V1 times V2 always has, P1 V1 has to equal P2 V2. So the pressure and volume always have to equal each other, well, equal the same value when they're multiplied together. So notice as volume goes down, pressure has to go up. So instead of being a nice straight line, we get a curve. So an isothermal process on a PV diagram is a hyperbola. Okay? P1 V1 has to equal P2 V2. So look at problem 29. Let's see, is that one gonna still work? Let's look at an isothermal process. Look instead at problem 37 on page 512. Okay, it's a real straightforward problem. I'm going to let you do that. These are some problems that would be a good idea for you to look at chapter 13. Now, I expect you to have gotten all the way through chapter 13 before we meet on Tuesday of next week. So, what? I'll look at that later. So, guys, go ahead and get all the way through this video, and then the next thing you'll get is a face-to-face lecture from me. See you then.